So the vapor pressure that we're talking about is one of the important properties of the liquids, is because we are talking about the boiling of the liquids, right? So if you have, the example that I give you is, you have water here, and if you have water here, and you keep it at room temperature, which is approximately 25 degrees Celsius, the evaporation is very slow. You know, the water is going to be in the vessel for days and weeks to evaporate actually. But when you apply more heat to this, it starts going to boil really quick, and you will see a lot of steam coming out of it. Means you are actually expediting the process of evaporation, which is also called vaporization. The liquid water molecules are converting into vapors, right? So, so if we look at this in a way that the water molecules are being converted into the vapors, will see very few vapors here, versus when you apply heat to it, you will see a lot of vapors, steam coming out of it. Okay, quickly, in minutes, in few minutes, you will see that this is happening. And at the time when it is 100 degrees Celsius of temperature, and you can keep a probe here, a temperature probe, to check what the temperature is, and you will see at 100 degrees Celsius, the water will start boiling aggressively, right? This is the time, this is the temperature where you have enough vapors generated on top of the water layer here, which will exert their pressure back onto the level of water. This is what we call vapor pressure. They were also doing it. Whenever vapors are generated, they put the pressure back onto the level of water. This is also called vapor pressure. But this vapor pressure is not equal to atmospheric pressure. We need more vapors here to make it equal to the atmospheric pressure, which is 760 torr. Okay, so that's not going to be equal. That's why we had to apply heat, so we can have more vapors, more pressure that can be equal to atmospheric pressure. So if atmospheric pressure at sea level is 760 torr, then we need to get this vapor pressure also to become 760 torr. And that is only possible if you have more vapors, more and more vapors generated on top here that can exert their pressure back, that is vapor pressure, onto the level of water, and that is the vapor pressure, and that becomes equal. This is the point when the atmospheric pressure equals, or the vapor pressure equals atmospheric pressure, is the point that we call the boiling point. This is where you will see that the water has started boiling here. So this is the story of vaporization, excuse me, vapor pressure and boiling. Okay, why water was not boiling at room temperature? We had to break the strongest intermolecular forces present between the water molecule, which was not possible at room temperature. You cannot break hydrogen bond between the water molecule. So we had to apply more temperature here, right? So that it's going to break the hydrogen bond interactions between the water molecules. Water molecules move faster and they go separated from each other. And that is the difference which we see from something going from liquid to the gaseous phase or the vapor phase, is that they are going to be at a larger distance. So if you have water molecules close by to each other, if you're able to separate them, right? If you are able to separate, have more distance between these water molecules, then this is actually not liquid. It's going to become the water or become the vapor, gaseous form of that sample. That's what we are doing with this boiling thing here. Okay, so vapor pressure and temperature definitely have a relationship. The higher the vapor pressure is, the more volatile the liquid will be. So if you compare the acetone that you use for as your nail color remover, so you put that one on your one hand, and then the second hand you put water. Which one is going to evaporate faster? Definitely acetone is going to dry up faster. That shows that even at room temperature, even at room temperature, what happened? You had enough, even at room temperature, the vaporization process is faster in acetone. And why? Because probably the weaker intermolecular forces are present there. Okay. So the weaker the attractive force is, the higher the vapor pressure. So if we boil acetone, it's going to boil at very low temperature compared to the water. So the intermolecular forces are playing their role. So small changes in temperature can make big changes in vapor pressure. There's a relationship that we are discussing here. We see that as we increase the temperature, the vapor pressure is going to increase. And that is a good relationship. But in chemistry, we want relationship to be linear. So what we can do, we can get this vapor pressure into the natural log and reciprocal of the temperature. And if we plot it, then we will have a very linear fashion between the pressure and the temperature. Okay, we need that. We need linear relationships so we can do the analysis really quick, and it's easier for us. So here it brings to the Clausius-Clapeyron equation. We have two different formats of the Clausius-Clapeyron equation where we plug the data in like we were doing it here. So we'll have different values of temperature, we'll have different values of pressure. We're going to convert those into L and P, and then convert it into 1 over T. And then we're going to plot these values like several values we had. And we got the linear relation. We're going to do the curve fitting. When we do the curve fitting, we get y equals to mx plus b. This is the equation that we get from the curve fitting. So this is the graphic form of the Clausius-Clapeyron equation, where y is equals to the natural log of vapor pressure. And this, if you separate this from here, it's going to be 1 over t, which represents x. C represents the y-intercept, which is plus b, and then h minus h over R, which is the enthalpy of vaporization, minus enthalpy of vaporization over R is going to be the slope. So we're going to get the value of slope. When we do the curve fitting, we get these two numbers from the graph here. Okay, when we do it in the Excel, we'll actually get that. Okay, so we get that from the graph, and then this is how slope is going to be equal to negative delta H of vaporization over R. And if we know the slope, the R is a constant, we can actually calculate the enthalpy of vaporization for the sample if we know the temperature, if we get the data of temperature and pressure for that sample. Different pressures at different temperatures, get the data for the sample, and then you should be able to plot that data into the graph on Excel, and you should be able to get the slope value from this y equation, and then plug that in to get the delta H of vaporization. Easy. This is the gas constant will be available to you in the exam. Here is an example for the second form of the Clausius-Clapeyron. There may be different rearrangement of the equations you will understand here. You may find an equation in different arrangements than to calculus because you can use it for different purposes. Okay. Here, what you see that you can use two data points to calculate things. Let's say if you change the temperature from one temperature to another temperature, what will be the change in the pressure there if you know the heat of vaporization for that particular sample. So the question here talks about water has heat of vaporization for the 1 kilojoules per mole. Vapor pressure at 373 K is 101.3 kP. What is the vapor pressure? So it's talking about the vapor pressure. Oops, sorry. The vapor pressure 1 is given to you. We'll just take it as pressure 1 and asking for the pressure 2. This is temperature 1. Okay, so this is pressure 1. Actually, I wrote it there, but I should have written it here. And then this is going to be your P2. This is going to be the P2 that you're trying to find out, and that's going to be your T2. Okay. So you must know that the value of R in joules, so the delta H is also be should also be converted into joules. It's given to you in kilojoules. Do not forget that. So we have converted that. And then temperatures are already given to us in Kelvin. So we're not going to, so if they were given to us in degrees Celsius, we were going to convert that into Kelvin. But it's already given in Kelvin. So just plug that in to the 2.2 data point equation. Okay, so this is our P1. And so you're going to solve this side and you're going to multiply and you're going to solve this also. And then you're going to multiply these two together. You're going to end up on this value. You're going to take the E function of the right-hand side's answer, which is this one. And in order to get rid of this ln, we take this E function on the right-hand side. So we get rid of the natural log on the left-hand side. So this has already been solved. Take the E function of this number in your calculator and then multiply that by this number, you will get the answer.